Now, as far as Dr. Wong is concerned, um, and we discussed it with him. IFSS combines fault trees and state charts effectively by converting a fault tree into a state chart and connecting it to all the components in the state chart. As far as the syntax conversion is concerned, that's done. That's complete. You don't have to worry about that. And we actually did our own example of that last year as well. We created an analog brake system model. We created the function. We created the system model itself, which is separate from the state chart, by the way. And that's also, by the way, a good way to make sure the fault tree and the state chart people are on the same page with terminology. Give them a system spec, a diagram of the system, because state chart is, while it's functional, it's different than just a system spec. But and if you look in our personal examples in the files, you'll see, an analog brake system model, visual model. Then you'll see the state chart, and then you'll see the fault tree. And we converted everything with syntax and everything. I mean, we did IFSS all the way through. But the thing that we're missing is proving that IFSS is necessary in the first place. What Dr. Wong told us is we need a situation, we need a model, a system that has a flaw that isn't obvious at all, but becomes obvious or is illuminated by using this method. Now, the counterintuitive nature of this is, on one hand, you want a model that you could explain to, or you could present to somebody to show them, simple enough that you can present so that they can understand, oh, I see how that works, without having to give them a full semester's course on it, or preferably without even having to give them an hour talk. 5 minutes, something familiar, preferably, something that they could kind of understand. You show them, this is the system, this is how it works, these are the separate models, the state chart and the fault tree. And then you try to demonstrate, you try to find something in the system that, had you not combined the two models together, had you not formally connected them and done formal testing, you would never have thought that the system could go wrong in that way. But what do you know? It did. So and the reason it's counterintuitive is, while you need to make it simple enough that you can explain it in a presentation, to make it so that the problem isn't easily detectable, you have to make the system a little bit more complex. I mean, you guys could just take our analog brake system and plug a few more features in here and there and make it harder to track, harder to understand, but still intuitive enough where people are like, oh yeah, I understand what's going on. But once a system gets complex enough, it's hard to track everything. So while when you're dealing with small systems, you can connect everything and you're like, oh yeah, I can see how that would be a problem or how that would be a problem. Once your system gets really, really huge and intricate, there may be situations that you would never think of that pop up, and you, by combining the two models together, can detect those situations. So, justifying the need for the combined integrated model, that's a huge step. So what we got so far, the syntax conversion is already taken care of. We just need to provide a legitimate example that shows we do need this combined system. We've already established why we're going with fault trees and state charts. It's because we're dealing with formal software, and we need rigidity and formality in safety intensive situations. We want to eliminate any doubt, and we've also established that state charts and fault trees are in use primarily in the same industries. So they're already there being applied. We just need to connect them together. If we do that, our system will be used. Now, moving on. And we've established that finding real examples of those state charts and fault trees will help you meet the designers, meet the users where they are, instead of designing something they're not ever going to use. Which brings me to my next point of research. There is a strong degree of natural language phenomena that occur when you're dealing with state charts and fault trees. Going back to our fundamental situation, any given safety intensive product or factory or whatever, what have you, you've got your functional people over here, and they're talking amongst each other. They're just trying to create a system that works. Then you've got your safety people over here, and they're also talking within the group, within their own group, trying to figure out how to ensure that the system doesn't fail in a catastrophic way. They don't want the system to screw up. These guys want the system to work. So these separate groups, the functional team and the safety team, are working really intensely together. But the way things happen most of the time is they don't communicate with each other. So they communicate within their own groups, but they don't communicate between the groups. The functional people don't oftentimes talk to the safety people nearly as much as they talk to each other. So you have a huge problem that can occur, and it's just what happens in natural language. People come up with their own terminologies. You're creating a new system. You're going to have different components and different events, and you've got two different types of minds working on these things. A safety engineer has a completely different perspective on a system than a functional engineer does. So they're going to even perceive things differently. So the fact that they would use different terms to describe a component or an event in the system comes as no surprise. So, I don't know, maybe it's something as simple as a trigger or a button. If you have different terminology for something, you can't understand each other. And that happens. You have different groups. And they talk to each other. They establish a common language among each other, but they don't establish a common language between each other. Now, why is that important? They have two separate terminologies. Here's why it's important. If you're trying to take a model from this corner and merge it with a model from this corner, and they're using two different sets of terminology for the same items, you're not going to be able to combine them. Not without serious manual work. Because you're going to have to read through the safety thing and say, well, when they say trigger, they really mean switch, or they mean button, or whatever it is. You're going to have to match those things up either manually or automatically. So, but the point is, they're not necessarily talking the same language and using the same terms to address the items, again, the components and the events within the system, the phenomena in the system. They may not be using the same language. And the way you connect those sets of terminologies, or ontologies as they're known, a set of terminology can be known as an ontology, is by using ontology matching. That's a huge thing. That was my own personal realization from last year from talking to some of the people in the Human Language Institute down the hall from you guys. Ontology matching is, I think, a study of like data modeling and human language, something of that nature, that tries to connect groups together, groups of terminologies together. They go through the terminologies and they see, well, this is a different word in this terminology than this word, but they're talking about the same thing. That's what we want to establish. We want to make those connections. And if we can make that as automatic as possible, which I can almost guarantee you is what ontology matching does, and I've included some papers, by the way, in the files about ontology matching, then the process of combining these models together can be streamlined. It's inevitable that the two groups are going to talk different languages with each other. And actually, because of the nature of fault trees, they're not nearly as rigid in the use of terminology. State charts are fairly rigid, but fault trees aren't rigid at all. You can write them as human-oriented or a state chart formally oriented as you want. So it's largely the safety side for which we need this ontology matching. But another way that you can get that common terminology is by using a common system specification. I think I already mentioned that. But ontology matching inevitably will become necessary. So that's how you can combine it together, combine the terminology.